Hello everyone. As Per said, I'm Sébastien, and I've been presenting before at Oslo, Trondheim, Cambridge, and very happy to be here this year in Bochum. This talk, as Per was saying, it's about VPNs, but not exactly. And it's a good example because the reason I'm doing this talk is nothing new, so hopefully I'm not boring anyone to death, but at the same time, it's also something that I see again and again is not known in the public domain, not known enough. So again, I was doing security consulting recently, and it would have solved, or at least seriously slowed me down, but in a matter of days, I was a domain admin on many networks, etc., and it was too easy. So hopefully what I present you today will help you avoid that kind of attacks. So in case you don't know already those abbreviations, a wide area network is just a big network, like typically between universities or different branch offices of a company. But also you might see on your home Wi-Fi modem, router, etc., it says one port. So it's one definition of it, and unfortunately then often people understand it as the internet. It's just the port to the bigger side of the network. Then you have on a smaller scale a local network, like your home network or a small business network, and you can recognize them, or often they are called LAN, meaning a private network. So all those IP addresses starting, with, like you would have at home, typically 192.168 and so on. And the 10 dot something is for the bigger networks, so mostly ones, but why not? You can also use it at home. I do. Then lately, especially in terms of wearables and people carrying around 3G dongle to have internet for their phone and laptop and everything, there's a term of personal area network, but it's basically the same as a LAN. It's just the idea is just for you, that it's just for you. The thing is, unfortunately, when you look at all that, and especially all these new trends of Internet of Things and everything in the cloud. So you have everything that's supposedly more convenient for you, like your printer, for example. HP is offering you to manage it for you, even not in terms of business, but for a home user. You don't have to worry about going to the shop for getting ink anymore. The printer is connected to their network, even though it's in your bedroom, for example, or office room. So technically, it becomes part of their network, and you don't realize you have all these devices in your home network that are actually parts of bigger networks. And lately, for example, you might have heard of a big denial of service attack that was performed by hacked cameras. So people were installing those cameras in their backyard or entrance or whatever to survey what was going on, but those actually were part of what's called a botnet, a large attack network or hacker network. And then you have all kinds of other considerations, especially as a company, in terms of disgruntled employees or contractors coming in and out, and all that new trend of bring your own device. So there's really no private network anymore. It's too many stakeholders. So my point is that you should consider all of them wide area networks anyway. And the one in the middle, also perhaps you don't realize, it's a especially tricky one when you have guests at your home and they ask you access to your Wi-Fi. So maybe you have split between your personal Wi-Fi and the guest Wi-Fi, but you have technologies, especially with Apple and Google, all the Wi-Fi passwords are saved in their cloud so that when you configure a different device, maybe you just bought an iPad, it already knows all of that you have configured in your iPhone, for example. But even further, what Microsoft had started doing, but then they had to revert that or not do it by default because people were were really angry about it, is that it would share, for example, if you give access to your Wi-Fi to a friend, then automatically within their social network, your Wi-Fi password would be also shared with their friends. So you're really losing control of your network, basically. So I don't know who is very familiar with networking, so hopefully I don't bore people, but it's a quick overview of basically what happens when you go and download software from download.com, which is apparently one of the most popular places to download Windows software. So what's going to happen is basically you will need all that information in green. Otherwise, your computer, I'll get into it, but you already have your own MAC address, and the rest is not important. So basically, you need to know where is the router, what is your own IP address, which is not something you carry with you. It will be different in the network here than in your network at home, for example, and where to send that request of download exactly. So first, you would have this DHCP protocol that you use all the time, perhaps without realizing, which gives you typically an IP address and the addresses of the servers for name resolution and default gateway. But those things are much more powerful. You can make computers boot a special different operating systems. So for example, typically backup solutions in enterprises would reboot computers at night and boot into a separate operating system to do the backup and so on. And other informations that I'll get back into later, but keep in mind this web proxy and static routes, for example. And also there's an older one, bootp, which is similar to DHCP, basically. So then let's say now you have an IP address on the network, but you don't really know if that network is directly connected to the internet or if you have to use a proxy. It used to be the case, especially in the beginning of public internet access, but it's still very much the case in companies. For some reason, many companies still use proxies, maybe for content filtering, so blocking access to certain kinds of websites, etc. So it's sort of not complicated, but not the most user-friendly. Once you have connected, then you have to configure different settings, etc. So web browsers, especially Microsoft and Netscape back then, have invented this web proxy auto-discovery protocol, which is enabled by default in basically all the browsers and other software like VirtualBox. And it's exactly what happens when you see that little box checked on the left, automatically detects settings. And technically what happens, your computer on the network is continuously asking, is there someone called WPAD, using different protocols to find that WPAD computer. So here it's a NetBIOS name resolution, and the other one is link local multicast name resolution, or it would use DNS and all kinds of things. But note also how often it does it. It does it pretty much several times per second. And in this case, there was no WPAD server to answer, so it just continues trying. And that's what all your computers are doing right now. Then let's say you have found a way, maybe you're directly connected to the internet, or you have to use a proxy, you got all that information, so now you type download.com. But to your computer, that doesn't really mean anything. So what it does first is it tries to find how to use that human name into an IP address. So I guess everyone's pretty much familiar with IP addresses, but basically it's sort of like a phone book. You get download.com and it gives you an IP address, this one in this case, or an IPv6, for example. Facebook has a funny one with Facebook in it. And also you have other protocols automatically in a local network. When at home, for example, you have probably not configured your own DNS server. You don't want to configure it all the time to say my iPhone is this IP address and my Xbox is this IP address, etc. So they have automatic configuration with various multicast or broadcast protocols like these MDNS and DNSSD, LLMNR, which is the one I was showing in WPAD earlier. And that's how, for example, when you have your own iPhone to which you give a name, for example, John Doe in this case, then automatically it creates a John Doe's iPhone.local, and that automatically broadcasts its name and IP address, basically. And those are compatible with DNS, and NetBIOS name resolution called the Windows Internet Name Service also in Windows networks is technically not the same, but it's the same idea. You ask it a domain name and it gives you an IP address if it exists. So, well, everyone knows what's an IP address. So in this case, a printer, for example. And then you use them to communicate between different networks. So, of course, it works within your own network as well if you're communicating between your computer and your printer or your phone or whatever. But also, it depends. It will work from your home network to the other side of the internet. Sorry. The problem is also that within a network, so while an IP address works from one computer to any other computer on the internet, technically at the lowest layer, directly to reach that computer across the cable, it's still not sufficient. You need a MAC address. And typically, or other kinds of protocols, but most likely a MAC address. And for that, you have the DNS equivalent. So DNS translates a name into an IP, and then ARP translates an IP into physical address. So that's how you would have, for example, this printer's IP address would become this kind of thing. So MAC address you find typically, for example, at the back of your Wi-Fi router. It would have two different ones because it has both a wireless interface, so you have to know how to communicate to that particular network card, or maybe you want to communicate to the wired card of that same router, so it's two different MAC addresses. And so you will use them within the network to communicate either directly with the target computer if you were trying to reach this printer within the same network, for example. But it's also how it works when you are trying to go to download.com or Google or whatever. You send a packet that has the destination of Google, but this destination of Google does not exist in your network. It's just being sent to the MAC address of your gateway here. So that's how the packet starts its journey. It's being sent directly to your router and so on. So that's the very basics of how it's all working. There's nothing special about that. But it also works very well as long as hackers don't start messing with it. So how do you prevent that? And then you have to go back into basics of crypto, or I don't know any other way of how to make sure that you're not communicating with the wrong person, and how to make sure that you're not letting the wrong person eavesdrop, overhear your conversation or see your traffic. It's the same, basically. So very basics of crypto. The symmetric one is the one that everyone is familiar with, even as children. For example, if you are in a classroom, maybe you are trying to send messages that you don't want the teacher to intercept. So you would use a variant, basically, of this Caesar cipher, where you're rotating letters and that kind of stuff. But that only works, it's called symmetric, because you have to agree with your friend in advance that all your letters will be rotated 13. For example, the typical one is called rot 13. So it's very simple, but it also poses a logistics problem, because then, for example, if you want to communicate with other friends in the same class and you don't want them to be able to see the messages with your first friend, so you have to agree with each different friend for a different key, etc. So it becomes difficult very quickly. And of course, you wouldn't do that with your bank, or you could do it with your bank. For example, if you went to the branch and agreed on a key for your banking transactions, but you wouldn't do it for every secure website on the internet, you know, Amazon, Google, Facebook, whatever. Would you go to the Facebook headquarters to agree on a secret key with them? Probably not. So what's really useful is then asymmetric crypto, which is a concept where instead of having one secret, one key that is shared between the both parties, each party generates two keys, one that is private and one that is public. And then you can give the public key to even the whole internet if you want, as long as you keep, of course, the private part private. And then the way it works is you send something to encrypt for a friend of yours, for example, you encrypt to them with their public key, so that they are able to decrypt what you sent with the corresponding private key. And then when they want to reply, so for example, in email, typically, they would then write to you, encrypt with your own public key, and then you can decrypt that with your private key, and so on. So then this is easy to understand for humans, but it works just as well for computers, devices, etc. So here you can be anyone or anything, can encrypt for anything with X is public key, and then it decrypts with their own private key. And so, sorry, the previous one, symmetric crypto, yeah, you must have heard of AES. It's a typically used nowadays for symmetric crypto. And the one typically used nowadays for asymmetric is RSA, or also Diffie-Hellman on HTTPS, etc. A really cool thing you can also do with asymmetric crypto, and it's recommended to not use the same keys for both purposes of encrypting and signing, but nothing, technically it's possible. So anyway, you can also do digital signatures, which allows you, it's much better than a handwritten signature that's so easy to forge if you're quite good at copying someone's signature. Whereas here you can publish anything and you add a signature as you would a human signature below it that everyone can verify that you wrote. But of course the idea is you don't want anyone else to forge that signature. So for example, that's what is in your passport most likely. You have all kinds of information about your photo, your height, your first name, last name, etc. And then what happens is, for example, I'm French, and the French government applied a digital signature to this passport information so that all the other countries I go to can verify that my passport was made by the French government and not forged by myself or whoever. But they don't have to reveal to the Americans or whatever other government what their private key is. However, all the other governments of all countries around the world can verify that signature. So a slight problem with that, with the asymmetric crypto is if you are not sure exactly who was processing the public key in the beginning. So ideally, for example, Alice and Bob here would meet in person, and Alice gives Bob her public key and vice versa. But on the internet, no one has time, etc. We want this to happen quickly, especially with all the secure websites you visit, etc. So you have to find a way of knowing that, for example, I am not between Alice and Bob telling Alice, yes, here is Bob's public key, which is in fact my public key. And then I would tell Bob, here is Alice's public key, which is also my public key. And then they are both happy thinking that everything is encrypted, but I'm actually decrypting everything and re-encrypting on the other side. So in order to find how to prevent that, there's a whole thing called the public key infrastructure, where everyone agrees on a limited number of trusted third parties. So, for example, you might have heard of GlobalSign, VeriSign, DigiCert, and all those things that your browsers and operating systems know about, which is how, for example, when you connect to Wikipedia, which is using HTTPS now, your computer doesn't, especially if you have never visited before, it doesn't know anything about Wikipedia. So how does it verify that the public key that you are given, pretending to be the public key of wikipedia.org, is actually really the original one? So what happens is you have a certificate. It's simply, it's a bit more complicated, of course, but you can think of it as a public key with some information about it. So saying, for example, this is the public key for anything on wikipedia.org, and it is digitally signed by someone that you or your computer already trusts. So in this case, for example, for Wikipedia, it's a GlobalSign. So like I said, your computer doesn't know anything about Wikipedia, but then it recognizes the digital signature of GlobalSign and it says, oh, okay, so I can trust that. And what's really nice about that also is that you can scale it. So for example, those really global certification authorities like GlobalSign, you would go one level under them, but if you do your own network or your own PKI for all purposes, so not necessarily just encryption, but also you can use it for code signing, etc. So you would have a root certification authority, which for which you would keep the private key very safe. So you would even put it in a physical safe because you rarely need to use it anyway. And then you make it so that it has vouched for, so it has written its digital signature onto the certificates of several sub-certification authorities. So, for example, you could have one for network encryption, one for email encryption, and one for code signing. So, for example, when you make programs, you can apply your digital signature so that people installing your program are more convinced that the program came from you. And then you can go several levels down, saying that, for example, the network encryption certification authority would split between the clients and the servers and so on. So, of course, not everything is perfect. So there's some pros and cons. The symmetric one, like I said, it poses a logistics problem, but to its advantage, it's really fast and very simple. So it's even considered somehow more secure than asymmetric keys, asymmetric crypto. That's why also you have symmetric keys that are usually shorter. So like 128 bits or 256 bits in symmetric is corresponding to much larger keys in asymmetric, like 1024, 2048, etc. Because the asymmetric one is much more simple. So it's much faster, but it poses a logistics problem. Then the asymmetric one is great for logistics because you don't have to know the public key, or you don't have to have agreed on anything with Facebook before the first time that you connect to them. But it's also very slow, very complicated, etc. So what happens most of the time is that you would use asymmetric as a first step to agree on a secret shared key that can also be temporary. So that's also increased security, so that you would use a different one for each connection, for example. And from there on, with that agreed symmetric key, you can do faster crypto. And also, having such a symmetric key agreed with the different parties that didn't know each other in the beginning, but thanks to asymmetric encryption can agree on the secret, you can have also something called the message authentication codes, which is like digital signatures, but much shorter and much quicker to do. Because as I was saying before, the digital signatures, it's a variant of asymmetric encryption. So it's also really slow. And you don't want, for example, when you are sending packets, encrypted packets on the network. You don't want each packet to be delayed a long time while each computer is signing the packet and the receiver is verifying the signature, etc. So what we do is a little trick where we make much shorter things that are apparent to signatures, but actually using symmetric crypto, so much faster. And to give you an example, so you would use in the first case RSA to agree using, so RSA is the asymmetric one that gives you the possibility to agree on the symmetric key. So that's what you use with AES. And then for integrity, you would use hashing algorithm that you might recognize here, the SHA-256. So it's basically hashing and encrypting with the secret that both parties know, but that an attacker wouldn't know. And you might notice it says 128 at the end. It's because it's so good in a way that it's different for each packet. So maybe a hacker would be able to crack the signature on just one packet after spending days working on it, but it's already too late. The next packet is using something different, etc. So it doesn't really matter. And you can even shorten it, make it smaller than SHA-256 would have an output of 256 bits, but you can even half it, and it's still secure enough. And that saves you from having, for example, you wouldn't want a lot of your 3G data plan paying money for just a bigger hash here if half of the hash is just as good. So going back to our installation from download.com, how do we prevent a hacker from messing with it? So typically in companies, you would have something, unfortunately not most often, switch partitioning is basically splitting physically or as if it were two different switches or more different switches, etc. But unfortunately, most of the time, what people refer to by VLANs, virtual LANs, is something called 802.1q, which is a logical layer. It's also called sometimes VLAN tag. And that's quite nice for doing some network separations between, for example, if you have VoIP phones and you want them to have a higher priority than the computer traffic, so that, for example, if someone starts a big download, it doesn't mess with, it doesn't kill everyone's telephone communications. But it's really not a security feature. It's you can hack around it. So another thing they could do to prevent a hacker from accessing the network, so sorry, I should have said on that first slide, the idea is that a hacker shouldn't be able to just pull a network cable and access everything. So maybe you have done some partitioning that says, for example, if I took the cable from a printer, I should be only able to mess with the printers. That would be already better than being able to mess with the whole network. Then you have something called port-based access control, where with different ways. So you have the MAC whitelisting, which is in Cisco parlance called port security, which is just checking if the MAC address, so the physical network address coming at the other end of the cable, is part of a whitelist. And as someone was mentioning this morning in the talk, it's easily spoofed. As you can see, I did it here. On Linux, you just need a command called MAC changer. Then you put whatever MAC address you want. And also that in MAC addresses, the first 3 bytes are actually assigned to different organizations. So for example, here the 5C260A belongs to Dell so that they can create lots of network cards and put whatever serial number at the end, and without risking conflicting with another manufacturer. And there's a funny range, this 002091, which belongs to the NSA. So hopefully they don't use MAC whitelisting to make sure that no one accesses their network, because you just need to do that to look like an NSA computer. Then another port-based access control system is 802.1x, which I strongly believe was plot by the manufacturers to get you to renew your network equipment, because maybe all the companies had already bought the nicest gigabit gear, etc., and it's all working perfectly, but we need to make more money, so we invent this new thing, or we market the fact that it's going to solve all your security problems, when in fact it's actually useless. However, it requires replacing all your switches, so it's quite good in terms of sales. What happens exactly is that when you connect to a switch that has 802.1x enabled, it's going to send you a challenge to say, okay, prove that you are a computer that's allowed to connect to this port. And as a hacker, maybe you don't have the necessary information to respond to that challenge, but nothing stops you from forwarding that challenge to a legitimate computer that's already part of the network, or a printer or something like that. Especially, for example, this is a Gumsticks embedded computer. So as you can see, it's 10, 11 centimeters long. It's something that you could really easily hide behind a network printer in a company. There's always a mess of cables behind that, and it would draw very little power, so you could even power it with a USB port of the printer or something like that. So that company might have 802.1x, making sure that only the printer is connecting to the switch. But so the switch would be here, for example, sending, okay, prove that you are the printer, and you just forward it to the other side, and the printer proves itself, so you just forward it on the other side, and now the switch is happy. So now you are in the network, both the printer and the hacker, and well, 802.1x is defeated. And one aspect of 802.1x that's even worse is this MAC authentication bypass. It's a mode where you can say, just for example, the printer, it actually doesn't really support 802.1x. So on certain switch ports that are configured maybe as a whole in the company would have decided to deploy 802.1x everywhere. But for some devices that don't support it, they would enable this MAB, authentication bypass. And then it means basically, well, it's just checking the MAC address, which we have seen on the previous slide. You can easily fake, etc. So you would even read it from a sticker on the printer or something, and there you are connected. No need to have a fancy hardware like that. Well, fancy, that's like $150, so that's really not that fancy. Then a way of correctly doing port-based network access control is MACsec, but that's a fairly new standard and unfortunately not widely adopted. So it's sort of like the same idea as 802.1x, where you connect your cable and the switch starts challenging you, but it doesn't stop at the very beginning. Once it's happy, it gives you the whole access to the network. It actually, you can even use encryption between the switch and the device connected at the other end of the cable. The problem, however, as I said, it's not that widely supported, especially I couldn't even find a printer that supports it. Whereas IPsec, for example, which I'm getting to, is part of IPv6. So if a printer supports IPv6, like most business printers do, then it would definitely support IPsec. And again, of course, you have to renew all your networking hardware to get that MACsec support. So then, of course, let's say maybe the hacker didn't get into the network by defeating those switch partitionings or 802.1q or 802.1x or MACsec or whatever. But there's still a way of messing with the network at the IP layer. So on the internet, I wrote a tool a long time ago that was part of Backtrack for some time, where you could see if you were able to forge packets from your network. But better yet, there's a whole, I forget, is it Center for Advanced Internet Data Research or something, sorry, I forgot the name, but they were monitoring all the IP spoofing on the internet, and that's typically done by denial of service attacks. They usually would prefer, the hackers would usually prefer that you don't see where the attack is coming from, but more and more internet service providers check that what you are sending to the internet looks like an IP address that's actually part of the network. So if you are spoofing the IP address, they would just drop the packet. But so it's trickier on the internet, but inside a private network or LAN or WAN or whatever, it can be as easy as just taking the IP address of the printer here. So of course, if you take it at the same time as the printer is still on, then you create an IP conflict in the network. But maybe as an attacker, you turned it off or you changed the IP on the printer, so you can still get around that. Or otherwise, okay, maybe you don't abuse the IP address of the printer, you just leave it to something else. So for example, this address resolution protocol that we were discussing earlier, it's also not secure. Most of all those protocols were invented before security was a concern. So the way it works, when ARP, so those are only replies here for simplicity, but if you remember at the beginning, a computer needs to know what address card, what network card has a certain IP address. So it would ask the whole network to ask who has this 47.1, for example. And then the computer that has 47.1 is supposed to reply and say, yes, I have it at this address, and so on. .2 is at this address, and so on. So that works nicely as long as no one is messing with it. But of course, if you look below the blue line, then here comes a hacker. You see the same MAC address on the right side claiming to be .1, .2, .200, and .254, most likely the router. So you can easily pretend to be everyone or whoever on the network using ARP cache poisoning. So okay, maybe you didn't do it at that level. So if you go further up, that's what Per is going to talk about in a while. But also DNS itself is not secure. So if you are being what is called a man in the middle, so intercepting and modifying the traffic of someone going to the internet, for example, and you tell them, well, actually download.com is 10.6.6, then their computer is going to say, well, okay, they don't see any difference. Same thing with IPv6. You can make it funny, like bad, disease, dead, whatever IPv6 address. So there's nothing in DNS that says this is legit or this is forged. There's no difference in it. That's what DNSSEC is for, and that's what Per is going to talk about. But the problem, of course, with it is that it's not widely used yet. So even funnier, if you haven't, if you think all the attacks that I only skimmed, because there's even more than that, so really local networking is crazy. But an even easier one to do is that web proxy auto-discovery protocol. If you remember at the beginning, that computer that was several times per second asking, is anyone the WPAD server? So it's continuously asking everyone, basically, does anyone want my web traffic? So if you are a hacker, you say, yeah, sure, send it to me. And then it's perhaps tricky to mess with the HTTPS traffic, but there's still plenty that goes in the clear, like I chose download.com, one of the most popular download websites for a reason also, is that what you download from it is not over HTTPS, it's over plain HTTP. So let's say a hacker just pretends to be in this network now, pretends to be the WPAD server, so basically your own proxy. They can modify that installer program that you downloaded and put a virus in it or spyware or whatever. That's by default, so really check your computers. It's in default in IE, Firefox, Chrome, VirtualBox, etc. So as I was saying, this all works as long as no one is messing with it, but basically this is how your trust in the network looks like. You can really tackle it at any point. So would you still run that downloaded Avast? That's the #1 download from download.com, as you can see, coming from HTTP. And I use Linux, so it would have opened it with Wine. But with everything that I have showed you so far, there's so many different ways that this antivirus is actually going to install a virus for you. So then you would say, okay, well, we have solved that problem. There's HTTPS and actually the whole protocol behind it, that SSL or TLS. But as Per would say, it's only one port or a couple of ports. You have still many other protocols that you would have to secure and double check that, for example, developers in a company network are not setting up some wiki or intranet site that asks you for your domain password in HTTP instead of HTTPS and so on. There's also all the network shares, Samba or NFS, etc. That's all in the clear unless I'm not even sure it's possible to encrypt them directly. There's a way in Windows Active Directory group policies that you can have some sort of integrity checks on the network shares, but it's still not encrypted as far as I know. So maybe a hacker wouldn't be able to modify documents that you are sharing, but they could at least see what you think was only between you and a colleague. Actually, the hacker that doesn't have access to these sensitive projects, for example, they would still be able to see all your documents. So as I was saying, often you have some little websites that are set up by teams on their own, and they have HTTP basic authentication, or all kinds of passwords transmitted in the clear. You also have all kinds of protocols that you are not sure are really secure. So some local instant messaging app, or all these new team collaboration protocols. And a funny one is these hashes sent to attackers. So you might have heard recently of the LAN turtle and what Sami Kamkar did with Raspberry Pi Zero, an equivalent, where basically when you connect a USB thing to a Windows computer that pretends to be a USB network card, and then Windows, even if the machine is locked, Windows is happy to have discovered this new network, and it will try to use it. And notably, it's going to try to find a domain controller or network shares, etc. And what you can do is you say, yeah, I'm the server, the file server with those network shares. And then Windows, to try to mount that network share, is going to send a hash of your password. So that what normally that Windows file server would do would be verify that you have indeed the right to access that folder. But when it's an attacker, it means now they have a hash to put into Hashcat or John the Ripper, etc. So that's really funny to do. So that's why today I want to talk about IPsec, which really is not only for VPNs. That's what most people know it for, but you will see it's not solving all the problems in security, of course, but it should solve, or at least make it much better than everything I have skimmed over so far. So the idea is, so instead of having to worry about all those different HTTP, DNS, whatever insecure protocols, you just put a secure layer below all of them, which is IP. So that's why it's called IPsec, for security of IP. Then there's different components to it. The authentication header is, you can use only that part. For example, if you, for some reason, you only want clear text transmissions, but make sure that no one modifies them, for some reason, if you want. Or most importantly, you would probably use this encapsulated security payload, which encrypts. So especially, you don't want to have encryption without authentication, or integrity, so that even if it's encrypted and a hacker cannot read directly what's being exchanged, it's not good if a hacker is able to mess with your encrypted traffic. So you would usually use a combination of VSP and AH. And also another option that's part of IPsec, I've never seen it used, but just so you know, you can even do compression with it. So that's what you normally see when people say IPsec. It's usually simply VPN, so typically between two different locations of a company, or from someone working from home and they want the laptop to be part of the company network to access the intranet, etc. So what's happening is you would have, for example, at home, your Ethernet or Wi-Fi layer, and then IPsec is the green part means encrypted. So whatever it's carrying inside, it's going to be protected by that green layer. So that's how then you send that to the other side of the network. So the other branch office or you're working from home to the company. You send a whole IP packet with whatever it was. So maybe you are trying to access the intranet, so it's IP, TCP, HTTP. And the gray part means it's insecure. But since it's protected, at least in that envelope, then it's fine so far. So in real life, actually, because everyone now has cheap networking equipment at home that's not supporting all protocols on the internet, etc., they are basically supporting only TCP and UDP, basically, for the network address translation. So that's when you are sharing your internet connection between several computers, as you would do now typically between your laptop, your mobile phone, and so on. And because then the router would be confused between what IP traffic, it wouldn't be able to redirect that directly to all the different computers. So what's typically done is this huge overhead of encapsulating everything into UDP, and then the same that I was showing just before. So that's called IPsec tunnel. It's when you have a whole IP packet inside of IPsec. That's what people are most familiar with. But what I want to talk about today mostly is the IPsec transport, meaning you can completely replace the IP layer here with IPsec, basically, so that you can have inside your home network, why not, but especially inside your company network, all the computers that are talking to each other, so the client workstations to the servers and so on, or maybe between client workstations as well, it should not be in the clear anymore. You should have this bottom layer that's just above Ethernet, of course, but that's securing everything that you put on top of it. So it doesn't really matter anymore if you have some developers doing a little website in the corner that's asking for passwords in clear text, because the password will be sent in clear text in that box here, but it's encrypted by the outer layer. As opposed to, oh yeah, it's actually not gray, sorry, it's red. Couldn't see from here. So yeah, that's the state of most networks now, unfortunately. So everything is insecure, basically. You have insecure Ethernet and everything I was presenting so far. So a hacker can mess with any of this, as opposed to this. So this is, let's say, a typical network. And in white, it's computers that are not configured to use IPsec. So let's say clear text computers. And they communicate with each other and so on. So what happens most of the time is this IPsec tunnel between a branch office here in some location and another office here in another location. So they still use two networks that are completely unencrypted. They just have this link between two gateways, two routers, that's encrypting here so that the NSA or some hacker at some service provider does not look inside the traffic. But the reality is that the hackers, they are here anyway. So that's the idea of using IPsec transport. You have the same company network or home network, if you want, and all the colored nodes are now using encryption. And that would be a hacker in the middle, or for some reason, a computer that was not yet configured. So for example, a contractor that just arrived and connected to the wrong cable, they cannot understand anything of what's going on. They cannot mess with the traffic around. So one really cool thing that you can do now instead of having to worry about proper physical separation of all the networks, which is really hard to do when you have networks that have evolved over many years, everything is connected to everything, and you would have to pull out all the wires and redo everything. Actually, with IPsec, you don't have to. You can still leave everything connected with everything, but you make it so that the different groups speak different languages if you want. So if you remember that public key infrastructure earlier, you would make it so that the green part would recognize certificates from a green sub-certification authority that the other colors would not recognize. So that, for example, let's say the blue node here would try to hack into the green computer here. Then the green computer would say, okay, prove yourself, what's your certificate, etc. So the blue computer would maybe try to give its blue certificate, but the green computer doesn't trust that green certification authority, so it would just reject it. And again, the hacker in the middle here doesn't know what's going on. So of course you would tell me, well, company networks are not that simple. We actually need to have links between different groups. You need to access printers and the canteen website and everything. And that's still possible. It's actually even better than what you could do with firewalls now, because if you remember what I was showing about that house of cards or cards castle, when you do packet filtering with firewalls, you're still trusting that whole house of cards. So you don't know if actually any of it has been spoofed. Whereas here with IPsec, you can really enforce proper firewalling, because here that cyan firewall here, it's a cyan as a mix of blue and green, because it would understand both those kinds of IPsec, let's say. But also there's no way that blue here, even by changing its IP address or forging DNS or whatever they would try, they could not communicate with the green one. They would still have to go through the cyan gateway. And then the gateway, once it's decrypted, you apply firewall rules here, and then there's no way that the traffic was messed with or forged, because it's only encrypted and signed by the real author. And of course then, what if you have printers or TVs or whatever devices that do not support IPsec? There are still some devices. Big printers usually support it, but maybe, yes, like I was saying, an Xbox for some reason or whatever. And especially the rest of the internet here, you wouldn't connect to Facebook or Amazon directly with IPsec. However, it would be much better to not have the hacker here be able to mess with all your internet traffic when you're downloading those, what was it, Avira or whatever antivirus from the internet inside the company network, and now you're installing that as administrator, but it's actually spyware, etc. So at least you would have all that secured directly to the border of your network here with a gateway that speaks all the different kinds of IPsec here, and then making it unencrypted for normal other networks like printers or the internet. So some excuses you will hear from people saying, oh no, IPsec, it's actually such an overhead on CPUs, etc. That's really not true anymore. There's a hardware acceleration of AES. Also in terms of overhead onto the packets, it's also negligible, especially on gigabit networks. You should be using jumbo frames anyway, which are up to 9,000 bytes. So it's really not going to slow down your downloads, your file transfers. You could make it even better if you store the private keys inside hardware security modules that most computers already have as part of the trusted platform module. And if it doesn't have a TPM, I think actually those Nitro keys are made in Bochum. So it's a 49 euros hardware security module on USB, etc. So of course, not something that you would put somewhere where there's a risk that someone would pull the USB thing, but it's also better than nothing for some router board somewhere in an enclosure or something. Then with TPM and some IPsec stacks like StrongSwan, you can do remote attestation, which is a way of securely verifying that no one has messed with the operating system on the other side, which you would typically do between two VPN gateways, for example, to make sure that maybe someone didn't modify the operating system. And to take it even further, you can make sure that even if, for example, in that blue network, you have different blue computers here. Unfortunately, I think Windows still doesn't support it, but you could have, so for example, the blue computer here couldn't pretend to be a green or red computer, which is already great if you have different sensitive network, classified networks, etc. But you could still have the blue computer here pretend to be this one, and you don't really want that. So there's an extension called X509v3 IP address, which is recognized by Linux and other Unisys, or BSD at least, but Windows doesn't really support it, so it would still be fooled by what I was just showing about the two blue computers, but Linux and BSD wouldn't. So that was a lot to take in. I guess I've tried to stay as simple as possible, but feel free to ask me questions now or come later on if you have some questions that come to mind. Any questions?